is? Guess what? That is a way we can measure pressure. All right, so as the air pushes down on the water, remember there's molecules hitting the water. Right? They're hitting the water, they're pushing down in the water, and then that pressure from the air pushes this column up. Now, if you were on the top of a really, really high mountain, then there would be less pressure, and possibly you might get a vacuum up here. All right? Now, turns out is if you were to make a column, this column is too short, if you were to make a column greater than 30 feet at sea level, at the very top, you would have a vacuum. Okay? Well, obviously it's not practical to make a 30-foot column of water, but we can use a more dense liquid. So scientists, instead of using water, would do this exact same trick and use mercury, which is 11 or 12 times, something like that, denser than water. And then the column turns out to be about 760 millimeters tall. That's at sea level. Here in Woodland Park, it's like 560. All right? In fact, yeah, let me show you how that works. So here I have an actual mercury barometer. So down here in the bottom of this is the vat of water, so to speak, but it's not water, but it's mercury. All right, and then we can see the mercury column tall and tall and tall, and we keep going and keep going. And we eventually reach this spot right here. And if you look at this spot, the top of the mercury line is about 565, it's just like 56.5 millimeters of mercury. And what's above this, it's empty space, so it's a vacuum. Because mercury is so much denser than is water, then we can, this is how you look at barometers. And the air pressure, all right, if you go back down here, right, think of the air pressure pushing down on this, and which forces the column of mercury up and up and up and up, all the way here in the park, to 56.5 centimeters, or 565 centimeters. Now that changes day to day. This is the pressure that we have today. All right, that was pretty cool. Now, that was with water, and of course water is not dense enough, and so scientists use, instead of water, they use mercury, and the mercury can only go up, because it's much, much more dense. It goes up to 29 inches, or 76 centimeters, and that is as high as it goes. This is at 1 atmosphere. In Woodland Park, it goes to about 500 and something. I think it's 580 on an average day. It changes because it's a weather issue, right? Okay, so how would you actually make a barometer? Well, first of all, you would fill a tube 1 meter long with mercury. You would then put your thumb over it. I wouldn't recommend that because, of course, that would it'd be a problem. Flip it upside down, and it would be completely filled. Okay, no, it wouldn't. It depends on your pressure. What you'd have up here is you'd have a vacuum. And below this would be equal to the height measured in millimeters of mercury. So if you are at sea level, this would be 760 millimeters tall, or 76 centimeters. Now, here in Woodland Park, we get like 580 millimeters, because, of course, there's lower pressure at our higher altitude. Okay, how do we do pressure conversions? Okay, well, first of all, 1 atmosphere is equal to 760 millimeters of mercury. You kind of heard me talk about that, haven't you? It's also equal to another unit we haven't gotten into too much detail, to call a kPa, or a kilopascal. That's 101.32 kPa. So let's see if we can do some pressure conversions. So let's practice some conversions. All right, so if I have 562 millimeters of mercury, how many atmospheres is this? Well, this is a very simple problem. We'll take 562 millimeters mercury, and we multiply. Remember our railroad tracks. I'll say there's millimeters of mercury in 1 atmosphere, and that number is 760. Notice I get the millimeters of mercury to cancel, so I get my calculator. So I'm going to grab my trusty calculator, and I'm going to take 562 divided by 760, and I get 0.74 ATMs, rounded to 2 significant digits. Probably should keep 3, so that's actually 0.739 atmospheres. All right, let's see if we can do one other one. Let's say that I've got 56.3 kPa, kilopascals, and I want to convert that to atmospheres. I can then say kPa to ATMs, and that's that 10 ATM, not AM, 101.32 kilopascals to 1 ATM, and I can say 1 ATM is 760 millimeters of mercury. We often like to convert to millimeters of mercury. So here, let me do that. 56.3 divided by 101.32 divided by, no, not divided by, times, well, I can't do things here, times 760, and I get the round figure of 422. That would be millimeters of mercury. Now let me say one more thing about millimeters of mercury. 1 millimeters of mercury, 1, is also equal to 1 torr. Okay, now torr stands for a famous scientist, Mr. Torlini from Italy, and he is the guy who invented the barometer. So, or Torricelli, it's Torricelli, and we just call it a torr. So Torricelli, so a millimeter of mercury. So I could just as well said this is 422 torr. Same thing. Okay. All right. Now, that was the kinetic molecular theory of liquids. When we talk about gases, actually this is kind of a cool picture to kind of illustrate there. I have 3 states of matter here in my liquids. Here we have gas, and they're just kind of flying around, and they're separated. And right here we have the substance as a liquid. And the liquid, you see the molecules, they're kind of roving around and they're closely packed. And in the solid, all they're doing is they're doing the vibration thing. Okay, so they're vibrating. These are just flying around and are not attached. These are sort of loosely attached. And these are, of course, liquid. So this is a liquid, this is a gas, and this right here is a solid. Okay? All right, so what's up with the kinetic molecular theory of gas? Let's talk about evaporation. Evaporation is an interesting thing. What happens when something evaporates? I'll bet you realize this. Here we have a steam bath. This is a hot area. I think it's volcanic in nature. And what is evaporation? That is going from any state to a gas, but not boiling. So if you're taking a shower in the morning and it steams up your shower, then you're having it from a liquid to a gas, but it's not boiling hot. It might be hot, and you might think it's boiling hot, but it's not technically boiling. If you poured boiling water on yourself, that would be ouch. Way ouch. Okay, and so here is kind of a way to look at this. Here we have a microscopic equilibrium between gases and liquids. Note the rate of evaporation of the liquid is equal to the rate of the condensation of the gas. And so what we've got here is we've got the liquids evaporating right here. You see? This is a liquid down here, this bottom part, and you see only a few get enough energy. Think of it back to our Boltzmann diagram. I'm sure we call it the Boltzmann diagram, but this diagram of kinetic energy, where this is the kinetic energy, this is the kinetic energy, and this is the number of molecules. And you see these ones right here probably, who are the average, cannot escape. But the ones that escape are the ones that have the higher energy. And so that would be the ones. So they have enough energy to escape the liquid state. Interesting enough, right here is a solid on this side of the picture. Now in this solid, sometimes even they also will have that same graph, right? This graph we're talking about. And just a few of them can escape. And this is the process called sublimation. When something turns from a solid to a gas. Okay, dry ice does this very well. Okay, in fact, well, here's a picture that kind of illustrates that. We can see which ones are going to escape. Maybe it's just these ones right here. And this would be, say, at 100 Kelvin, at 1,000 Kelvin. How many would actually escape there? Well, it would be all of these, wouldn't it? Anybody above a particular amount. So let's say that only these above this line can escape. Well, if you are at 1,000 Kelvin, a lot of them will escape, almost all of them. And this one, very few on the blue line. All right. What about vaporization? Well, vaporization is liquid to a gas, but it can either be evaporation or boiling. I want you to kind of understand there's a difference between vaporization and evaporation and actually boiling. So either boiling or evaporation are both considered vaporization. All right. Now what about vapor pressure? A new term. Lots of different sort of words to describe. What you should definitely do is draw some pictures as you do this, okay? All right. Vapor pressure is the pressure exerted by a liquid as it evaporates. So again, think of our picture right here. These particles, as they evaporate, right, they hit so if the ball, ouch, hits me in the head, it exerts a pressure. All right. So if I have a sealed container, so think of this as like an aquarium right here, and we have water, right? And here we have the water, and some of it is evaporating. As these molecules move to the outside, they exert a pressure. They're hitting the outside. So they have a particular thing called the vapor pressure. All right. Some more definitions. All right. What do you think? The higher the temperature, about terms of the vapor pressure, the blank the vapor pressure. What do you think? If it's going faster, think. That's right. It will be higher. Yes, indeed, it'll be higher. Oh, I haven't even wrote it there. That's cool. All right, so a lot of definitions in this podcast, and this will kind of get us an understanding of how things work. Next time, we're going to talk about something, maybe the coolest demo of the year. We're going to talk about boiling, and I'm going to be able to boil some things. Boil. I will boil some things that are cold. Oh, man, that's so cool. Okay, so that ends. I guess Mr. Sams could not pop in today because he is so busy with students. It's finals week, actually, and I don't